Hi everybody. Okay, so I wanted to go over some of the questions from the homework in physics. This is from Unit 3 where we were reviewing X-ray production and going over some things regarding half-value layers and those things related to blocking and radiation protection. So this is from Unit 3. And you had 2 assignments, or more than 2 assignments, but I especially want to go over a couple of questions in homework number 3. On the top of it, it said Unit 3, Review of X-ray Production. I want to go over a couple of questions from homework number 3. The ones I want to review are the ones that seem to be the most challenging for the majority of the class. Then I want to go over homework number 3A. But first, homework number 3. So question number 7 was about calculating a new reference dose rate. So in the question, they gave you a reference dose rate measured at a distance of 80 cm. This distance would be from the source, whatever the source of radiation. Like, since we see this dose rate is in exposure in the air per unit time, this is probably talking about a live source like the cobalt. And then they asked you to calculate a reference dose rate at a different distance. So now what we have to remember now, or have to recall in order to solve this problem, is the relationship between dose rate and distance. So dose rate is like an intensity. And the dose rate, or this intensity and distance, have an inverse relationship. That is, the closer you are to the source, the more intense, or the higher the dose rate. The further away you get from the source, the lower the dose rate. You increase the distance. As distance increases, dose rate decreases. And dose rate is like an intensity. You can express intensity of the X-ray beam by talking about its dose, or its dose rate, or exposure, and exposure rates. Okay, so what we're going to need here is the inverse square law. So I use the inverse square law, and this before I even calculate it, I should really think about what the answer should look like. Because according to that law, as you increase the distance, the intensity is going to decrease by a square of the distance change. So if I have a dose rate of 52 Roentgen per minute at a distance of 80 cm, this new dose rate at this increased distance should be smaller, should be less than 52 Roentgen per minute. So maybe already, if this were a multiple choice question, I should be able to eliminate any of the answers that would be greater than 52 Roentgen per minute. I can look and see how much the distance has changed. To go from 80 to 100 cm is how much of a change? That's about a 20% change. So I know that this is going to change in the reverse at least twice that. Now, doubling is not the same as squaring, and there is a square in this formula, so you have to remember to use the square. But at least thinking about it that way puts you in the frame of mind of what the answer should be like. So I'm going to use the inverse square formula. I like to write the formula out flat like this. And remember, the squares only belong to the distances. So the first intensity is the 52. The second intensity is what I don't know. The first distance belongs to the 52. The second distance belongs to the new intensity that I don't know. So this is the way I'm going to set this up. And then I'm going to plug in and solve for X. So the answer should be around 33.3 Roentgen per minute. Okay, the next question, number 8, was about, this is an exercise on how we understand half-value layers and what half-value layers do to intensities. So this reference to 10 packs of energy could be like an intensity, could reference the energy of the beam. And so we know when we have a half-value layer, one half-value layer would reduce that intensity, or whatever it is we're talking about, that characteristic. The number of photon packets would be reduced if I have one half-value layer of a material by 50%. Two half-value layers would reduce that by 25%. You're familiar with this, right? So in the question, they're saying that these 10 packs are on 1.5 centimeters slab of material. And this 10 packs, this energy, whatever this intensity, has a half value layer already established at 1.1 centimeters of slab material. How many packs of energy are going to be transmitted through the 1.5 centimeter slab? So we can use what we know about half value layers, and if this had multiple choices, I can't remember if there were multiple choices on here, but just think about one half value layer is the 1.1 cm. That would reduce us to 50%. Or we'd have 10 packs, that 1.1 cm of slab would be here. On the other side, what would be transmitted would be 50% of 10, which is 5 packs. And then if we had 2 half value layers, then whatever I started with, the 10 packs, would be 25% of the 10 packs. In measured distance or slab of material, this would be 2.2. I got the 2.2 by stacking half value layers. 1.1 and 1.1 is 2.2 centimeters of material. Now at this point, I can go back to the question and say they're asking me about a 1.5 cm slab, which is not 1.1. It's more than 1.1, which is not 2.2. It's less than 2.2. So the amount of packets that come out on the other side of the slab has to be somewhere in between 50% and 25%. And maybe this helps me eliminate some of the other answers if this were multiple choice. But in order to calculate this, I can use a direct proportion because half value layers and amount of material, half value layers, and the number of slab centimeters is directly related. The more material I have in slab value, the more material, the more half value layers. That's a direct proportion. So I can set this up as a direct proportion like this, and then come up with this answer where I actually have 1.36 half value layers of material. I don't have 1, I don't have 2, I have 1.36 half value layers. Now the next step here would be to understand, like, what do I do with the 1.36? Well, increasing half value layers is also like raising halves. So 1 half value layer would be like a half raised 1 time. 2 half value layers would be a half raised 2 times. 3 half value layers, a half raised 3 times, and so on and so forth. If you put this into your calculator, you'll notice that you'll get these percentages. Mathematically, that's what these mean. So I could take the half to represent 1 half value layer and raise it 1.36 times. You could do this in your calculator and you come out with this answer. 0.39 expressed in a percentage is 39%. So on the other side of 1.5 centimeters, I'll have remaining 39% of where I started. 39% of 10 is 3.9. The other way I could solve this problem, though, is to use the intensity formula, which you remember looks a lot like activity, but half value layers, this principle of half value layers helps us approximate. It is not exact, not absolute. We know that the half value layers and intensity actually have like a logarithmic relationship. And here's the formula. Yeah, I think you're used to seeing it like this. This is the way we learned it in class, like this, laid out like this. But what I've done is I've taken the first intensity and just moved it to the other side of the equation. So I get this. So intensity over intensity. This is the beginning intensity. This is the ending. When I put those in a relationship, a ratio, I get transmission. From this formula, intensity from the beginning and intensity at the end is also equivalent to this. This E, this base E, raised to the negative mu times x. Remember, mu is the linear attenuation coefficient, and we have a formula for that. So I could solve for mu. Here's the formula, natural log of 2 over the half value layer. Natural log of 2, half value layer. This is what mu is. Now I can substitute mu into this portion of the formula and figure out what this side of the equation is equivalent to. So I get this answer as the mu. I put the mu there. The actual thickness of the slab is here. When I multiply those two, I get this. When I do this in my calculator, e raised to the negative, don't forget to put the negative, this is the answer I get. So I've gotten the transmission. This is the transmission. You could think about this as percentage, the same way as we think about this as percentage. This is 38.87%. Further, I can go and calculate. Now I can take this a step further. Instead of just saying, okay, 38.87% of 10 is 3.887, which is about 3.9, almost 4. Well, go ahead and substitute the 10 packs as your starting intensity. There's the 10 packs. I don't know how many packs I have at the end, but this is the transmission. This ratio relationship gives me transmission. So I'll have the 10 packs here, X there, and then what I've calculated on this portion of this formula. And I get 3.887. So the answer to number 8 is about 4 packs, 3.887 packs if we solve it this way. 3.9 packs if we solve it that way. Okay? Hope that helps.